Physics is the science that unveils the deepest mysteries of the universe, revealing how the smallest particles shape everything around us. At CERN, the world's largest particle physics laboratory, scientists constantly push the boundaries of knowledge, unlocking groundbreaking discoveries like precision measurements on the Higgs Boson and the effect of gravity of antimatter. But what happens when a discovery comes along that could change everything we know about the universe? Join us as we dive into the chilling new discovery that CERN scientists have just broken their silence on, a revelation that changes everything. CERN, pioneering particle physics. The European Organization for Nuclear Research, or CERN, is a leading institution in particle physics, founded in 1954. Based in Meyrin, Switzerland, CERN has grown into the world's largest particle physics laboratory, playing a pivotal role in advancing our understanding of the universe. Created in the post-World War II era to foster European scientific cooperation, CERN has become a global hub for research and discovery. One of CERN's earliest milestones was the creation of its first particle accelerator, the 600 mega-electron-volt synchrocyclotron, SC, in 1957. Though modest by modern standards, the SC laid the groundwork for CERN's groundbreaking experiments in particle and nuclear physics. Early on, scientists used the SC to test the existence of the pion, a particle predicted to decay into an electron and neutrino. Within hours of starting the experiment, they captured the first clear evidence of this rare decay, propelling CERN into the global scientific spotlight. As research progressed, CERN's focus expanded. In 1959, CERN introduced the proton synchrotron, PS, a more powerful accelerator that enabled higher energy particle interactions, marking the beginning of an era of significant breakthroughs in particle physics. In 1967, CERN further expanded its research with the construction of the ISOLDE facility, designed to produce and study radioactive ions. ISOLDE became essential for research across various disciplines, including nuclear physics, medicine, and astrophysics. One of CERN's most groundbreaking accomplishments came in the late 1960s with the development of the intersecting storage rings, ISR. In January 1971, the ISR made history by colliding two proton beams for the first time, marking the birth of hadron colliders. This innovative approach, where particles collide head-on rather than striking a fixed target, enabled much higher energy interactions and was a crucial step in the development of future accelerators. The ISR's success led to pioneering techniques like stochastic cooling, which continues to influence modern accelerator technology. CERN's advancements, particularly with the ISR, set the stage for future projects, most notably the Large Hadron Collider, LHC, pushing the boundaries of particle physics and revolutionizing scientific research, building on the groundbreaking achievements of the ISR, which set the stage for future advancements in accelerator technology. CERN's work continued to evolve. This progress culminated in the creation of the Large Hadron Collider, a machine far more powerful and sophisticated, designed to delve deeper into the mysteries of the universe. The power of the LHC. The Large Hadron Collider, LHC, is one of humanity's most ambitious scientific undertakings, a colossal machine designed to probe the deepest mysteries of the universe. Nestled underground at CERN, the LHC is the largest particle accelerator in the world, with a massive 27-kilometer circular ring. But what does it do, and why is it so crucial to our understanding of the universe? At its core, the LHC is a collider, a machine that accelerates particles to nearly the speed of light and then smashes them together. This process mimics the conditions of the Big Bang, allowing scientists to recreate and study the forces that shaped the universe from the very beginning. Why is this important? Because the universe is governed by fundamental particles, and understanding them is key to uncovering the laws of physics. By studying the particles that emerge from these high-speed collisions, scientists gain insight into how the universe functions at its most basic level. The LHC operates as a circular tunnel, inside of which two beams of high-energy protons race in opposite directions. These beams travel at speeds just shy of the speed of light, 99.999999% to be exact. To reach these speeds, the LHC employs a fascinating technique involving radio frequency cavities. These are special tubes placed throughout the accelerator that generate alternating electric fields. Each time a proton passes through one of these cavities, the electric field gives it a little push, propelling it faster and faster until it reaches its nearly light-speed velocity. As the protons accelerate, one might wonder, why don't they fly off in straight lines? This is where the LHC's ingenuity shines. Protons, like all particles with an electric charge, naturally follow a straight path unless acted upon by a force. To keep these particles moving in a circle, the LHC uses a powerful system of magnets to bend their trajectory. At first glance, it seems counterintuitive. Magnets don't accelerate particles, they deflect them. So how do magnets keep these protons on their circular path? The answer lies in the strength of the magnets. The LHC's magnets are so strong that they can bend the path of particles moving at nearly the speed of light. These magnets work by creating intense magnetic fields that push and pull the protons into a circular orbit. The strength of these magnetic fields is mind-boggling, 8 Tesla. To put that into perspective, the Earth's magnetic field is only 0.04 Tesla. To create such powerful magnets, they need to be in a special superconducting state, which allows them to operate without losing any electrical energy. This superconducting state can only be achieved at incredibly low temperatures, about -271.3 degrees Celsius. To reach such frigid temperatures, the magnets are submerged in liquid helium, which keeps them cold enough to function properly. Once the protons are traveling at near light speed, the LHC's job isn't over. The next step is to get them to collide. The two beams of protons meet at 4 designated points along the ring, where massive detectors have been installed. These collisions are where the magic happens. When the protons crash into each other, they break apart, producing hundreds of new particles. This is where scientists can make their most exciting discoveries. But detecting these particles isn't as easy as it sounds. The particles produced in these collisions are fleeting. They exist for only a fraction of a second before decaying into other particles. To capture these fleeting events, CERN has built some of the largest and most advanced detectors ever created. The two largest detectors, ATLAS and CMS, are designed to capture a wide range of data from each collision, studying the properties of the particles created and helping scientists identify unknown particles. Then there's ALICE, which specializes in studying a state of matter called quark-gluon plasma, believed to have existed in the early universe just moments after the Big Bang. Finally, the LHCb detector focuses on understanding the subtle differences between matter and antimatter, a question that may hold the key to why the universe is made of more matter than antimatter. These 4 detectors, ATLAS, CMS, ALICE, and LHCb, are at the heart of the LHC's scientific mission. Together, they provide insights into everything from the fundamental building blocks of matter to the very fabric of space-time itself. To unlock these mysteries, the LHC not only accelerates particles to extreme speeds, but also collects a vast amount of data from every collision. This massive influx of information is crucial in driving discoveries like the Higgs Boson and furthering our understanding of the universe's most fundamental questions. Cracking the universe. Among the most remarkable discoveries made by experiments at the LHC is the Higgs boson, famously confirmed in 2012. This elusive particle, often referred to as the God particle, is crucial because it gives mass to all other particles, making it fundamental to the way matter behaves. But the search for the Higgs, along with countless other groundbreaking experiments, requires an immense amount of data processing and analysis. Every second, the LHC generates around 1 billion particle collisions, each one potentially yielding hundreds of new particles. The real challenge, however, lies not only in capturing this data, but in sifting through it to find the rare, interesting events hidden among the noise. 2 key experiments at the LHC, involving ALICE and LHCb, demonstrate the diversity of research carried out in this particle collider. ALICE focuses on studying quark-gluon plasma, a state of matter thought to have existed just moments after the Big Bang. This plasma is made up of quarks and gluons, the fundamental building blocks of protons and neutrons, before they combine to form the matter we know today. ALICE aims to recreate and study this primordial soup of particles, offering insights into the early moments of the universe's history. Meanwhile, LHCb investigates one of the most profound mysteries in physics. Why is there more matter than antimatter in the universe? Theoretical physics suggests that the Big Bang should have created equal amounts of matter and antimatter, but observations show that the universe is overwhelmingly made of matter. LHCb's goal is to uncover the subtle differences between matter and antimatter, possibly revealing why the universe took the shape it did. These experiments are far from simple. The LHC generates an overwhelming amount of data that requires sophisticated systems to process it. Every second, 1 billion proton collisions take place inside the LHC's detectors. Each collision produces a variety of particles, but only a small fraction of these are useful for scientific analysis. Given that over 99.9% of the data produced in these collisions is irrelevant, the detectors must be able to select and record only the most important events. The data generated by the LHC is staggering. More than 1 million gigabytes of data are recorded every day, equivalent to filling over 1,300 modern 1 terabyte SSDs. But capturing this data is only the beginning. The real work begins when scientists analyze it to uncover new discoveries. This process is similar to finding a needle in a haystack. For example, in the search for the Higgs boson, researchers had to identify very specific signatures that would indicate the presence of this particle amid the collision debris. So how do the LHC detectors know what data is worth recording? They rely on a combination of high-tech systems designed to track particles with incredible precision. Take the CMS experiment, for example, which is one of the most complex detectors at the LHC. It is made up of several sub-detectors, each with a specific purpose. One of these is the tracker, which tracks the trajectories of particles. The tracker is made of silicon layers that leave traces when charged particles pass through them. These traces are then used to reconstruct the particle's path, allowing scientists to know where it originated and how it moved. Another critical sub-detector is the calorimeter, which measures the energy of particles. Made from lead tungstate crystals, the calorimeter detects the light emitted when a particle passes through it. The amount of light produced allows scientists to infer the energy of the particle. Together, the tracker and calorimeter, along with other detectors, provide essential data on the particles produced in a collision, which researchers can use to identify potential new discoveries. Once the data is collected, the real detective work begins. For example, to find the Higgs boson, scientists know that they must look for a specific signature that the particle leaves behind when it decays. The Higgs boson decays almost instantaneously after being produced, often into 2 photons, particles of light. These photons have a unique signature in the detectors. They don't leave any marks on the tracker, but produce a burst of light in the calorimeter. However, distinguishing the Higgs boson's decay photons from the many other photons produced in the collision is no simple task. To separate the signal of the Higgs from background noise, physicists must consider additional factors such as the energy and direction of the photons. The photons from the Higgs decay typically behave differently from those produced in other processes. This is where advanced algorithms come into play, sorting through massive amounts of data to isolate the Higgs signal. Despite the complexity of the task, this methodical analysis paid off when the Higgs boson was finally detected after decades of searching. But the work doesn't stop there. Redefining physics. The LHC's experiments produce a staggering amount of data, nearly 15 petabytes annually. This volume is so vast that it is equivalent to storing 250,000 films for each petabyte. Over time, the LHC has amassed more than 200 petabytes of data, a treasure trove that continues to drive groundbreaking discoveries. Among the most fascinating revelations made possible by the LHC is the evidence for quarks, the fundamental building blocks of matter. These particles come in a variety of flavors, and their interactions are central to the structure of the universe. However, some quark types are highly unstable, decaying almost instantaneously into other particles due to their immense energy levels. Beauty quarks, for instance, exist for an infinitesimally brief moment, between 1 and 2 trillionths of a second, yet hold a wealth of secrets about the fabric of reality. Recent data from the LHC challenges long-standing assumptions about quark behavior. Conventional physics predicts a specific pattern for how quarks decay into particles such as muons and electrons. Yet, the observed likelihood of quarks decaying into muons compared to electrons deviates from expectations. This discrepancy suggests that unknown forces may be at play, hinting at physics beyond the Standard Model. The Standard Model has long been the cornerstone of our understanding of particle physics, providing a framework for describing the interactions of the universe's most fundamental particles. However, it is incomplete. While it explains 3 of the 4 fundamental forces, electromagnetic, strong nuclear, and weak nuclear, it fails to account for gravity or the elusive dark matter that is believed to make up much of the cosmos. The anomalies observed in quark decay rates have prompted some scientists to hypothesize the existence of a new particle or force that interacts subtly with electrons and muons. They speculate about an energy carrier dubbed the Higgs Boson, a particle so faint that it has yet to be detected. If confirmed, this discovery could expand the Standard Model and provide critical insights into long-standing questions about the universe, including the nature of dark matter and the mysterious role of the Higgs boson. These findings are not just theoretical curiosities, but represent a potential step toward one of physics' grandest ambitions, unifying the fundamental forces of nature into a single cohesive theory. This theory of everything has been a holy grail for physicists for decades. The discovery of a new force or particle could bring us closer to achieving this unification and resolving inconsistencies within existing models. The possibility of such groundbreaking advancements underscores the importance of the LHC, which remains the world's most powerful particle collider. It is a global effort, involving over 10,000 researchers and contributions from hundreds of institutions and laboratories worldwide. As the LHC continues its quest to unify the fundamental forces, it pushes the boundaries of our understanding, with scientists on the verge of unraveling the universe's deepest secrets. This next breakthrough could provide the key to unlocking mysteries that have eluded physicists for centuries, offering new insights into the cosmos. A groundbreaking discovery. In a groundbreaking achievement, scientists at CERN have for the first time identified high-energy neutrinos produced by the LHC. This significant milestone in the field of particle physics comes with the discovery of 53 neutrino interactions, marked by exceptional accuracy. This breakthrough not only opens the door to understanding the universe's most mysterious particles, but also promises to shed light on some of the most profound cosmic phenomena, such as the intense neutrino interactions that occur in the hearts of stars and the explosive forces driving supernovae. Neutrinos are among the most elusive and enigmatic particles in the universe. These tiny, massless particles, which carry no electric charge, are constantly streaming through space and interacting with matter in nearly undetectable ways. Every second, an estimated 100 billion neutrinos pass through each square centimeter of our bodies. Yet, because of their ghostly nature, we are completely unaware of their presence. It's this near invisibility that has earned them the nickname ghost particles. Neutrinos are created in a variety of ways. When atomic nuclei fuse or break apart, in the aftermath of radioactive decay, in cosmic ray interactions, and within the high-energy environments of particle accelerators and nuclear reactors. They are even produced naturally through processes like the decay of potassium in bananas. Despite their widespread existence, neutrinos are notoriously difficult to study due to their weak interaction with matter. As a result, detecting them requires highly sophisticated and precise technology. Scientists have been chasing these elusive particles for decades, ever since their first detection in 1956, when they were observed emerging from a nuclear reactor. Fast forward to 2021, when researchers managed to spot 6 neutrino interactions, providing the first solid evidence of their presence in a collider experiment. However, confirming their existence took 2 more years of careful analysis and data collection. According to James Boyd, a particle physicist at CERN and co-spokesperson for the phase collaboration, this discovery is a monumental step forward. Ghost particles can teach us about deep space in ways that other methods cannot, he explained. The identification of high-energy neutrinos at the LHC is particularly exciting because it opens new possibilities for studying the universe's most extreme environments. These high-energy neutrinos may hold the key to understanding some of the most intriguing aspects of particle astrophysics, such as how stars burn and explode in supernovae, producing vast amounts of energy and neutrinos in the process. Neutrinos may also provide insights into the mysterious workings of black holes and other cosmic phenomena that we currently only hypothesize about. The project, which will continue collecting data until the end of 2025, has already sparked a wave of excitement in the scientific community. As more neutrino interactions are detected, physicists expect to uncover new and unexpected findings that could challenge our understanding of the universe. Each discovery brings them closer to unraveling the mysteries of these ghostly particles and, by extension, the fundamental forces that shape the cosmos. In the years to come, neutrinos could become crucial messengers in the quest to understand the deepest questions about the origins and workings of our universe. Now it's time for today's subscriber pick. In the heart of the CERN laboratories, Dr. Eleanor Hartman stood before the control panels, her fingers trembling slightly as she reviewed the data. For weeks, something unusual had been detected deep within the Large Hadron Collider. A particle, unlike anything they'd ever encountered, had appeared in the streams of data, flickering in and out of existence with an unpredictable intensity. No one could explain it. Could it be? She whispered, staring at the glowing screen. The mysterious particle had shown properties that defied all known laws of physics. It wasn't just a new particle, it seemed to interact with gravity in ways they had never imagined. News of the anomaly spread quickly through CERN. The team worked around the clock, running simulations, collecting data, and rechecking their findings. It wasn't long before the word was out. CERN scientists were on the verge of a discovery that could rewrite the rules of the universe. Then, just hours ago, Dr. Hartman had received a message from the lead physicist, Dr. Michael Adler, who had called an emergency press conference. The message was clear: CERN scientists had finally broken their silence on the chilling new discovery that changes everything. The particle they revealed wasn't just a glitch in the system. It was evidence of a parallel universe, one where the laws of physics were dramatically different. This discovery, they claimed, could hold the key to understanding the very fabric of reality itself. As the world listened, Elena couldn't help but wonder, what did this mean for humanity's future? But while the scientific community celebrated the groundbreaking discovery of a parallel universe, the world outside CERN was abuzz with a different kind of speculation. The web of conspiracy. The LHC has long been a magnet for conspiracy theories. One of the earliest and most prominent conspiracy theories surrounding the LHC was the fear that it could create a black hole so massive that it would eventually collapse the Earth. The idea was based on the notion that smashing particles together at near-light speeds could somehow create a miniature singularity. However, despite these fears, no such catastrophe has occurred. In fact, CERN scientists, aware of the speculation, spent years reassuring the public that their research was perfectly safe and that the formation of a dangerous black hole was highly unlikely, if not impossible. Nevertheless, these reassurances did little to quell the imaginations of conspiracy theorists. In the early 2000s, as CERN's groundbreaking project experienced delays and setbacks, a particularly bizarre theory emerged. Some speculated that the LHC's failures were the result of sabotage, deliberate interference from a time traveler from the future. According to this theory, the time traveler was desperately attempting to stop the collider from operating, fearing that the consequences of its activation would be disastrous. The strange part of the story involved a time-traveling bird, supposedly carrying a baguette, that was purportedly part of the sabotage attempts. While the specifics of the theory were certainly outlandish, the core idea that the LHC's power was so immense that it could be the catalyst for a catastrophic event remained central to many conspiracy narratives. But time travel is hardly the only wild theory circulating about the LHC. Another, perhaps more widely known theory suggests that CERN is secretly opening portals to other dimensions, or even hell itself. These theories gained traction after CERN announced that it was experimenting with creating microscopic black holes in the hope of studying antimatter. The idea of creating black holes, even on such a small scale, raised alarm bells for those who worried about the potential dangers of opening gateways to parallel universes or otherworldly realms. In early 2024, the LHC was once again at the center of a new round of speculation. This time, conspiracy theorists pointed to the coincidental timing of CERN's experiments and the 2024 Great American Eclipse, a total solar eclipse that would be visible across North America. While the LHC regularly conducts experiments and particle collisions on any given day, some suggested that the activation of the collider on April 8, 2024, was somehow linked to the eclipse, which some saw as an event of cosmic significance. Theories emerged that CERN might be attempting to harness the energy of the eclipse to open a portal to another dimension, or even make contact with extraterrestrial forces. One particularly outlandish theory connected CERN's activities to the occult. According to one theorist, the infamous British occultist Aleister Crowley had made contact with a demonic entity named Aiwass on April 8, 1904, and CERN was now trying to repeat this contact through the LHC. The theory suggested that CERN's experiments, occurring on the same date as Crowley's alleged mystical encounter, were an attempt to summon dark forces from another realm. While the connection between a total solar eclipse and occult practices is tenuous at best, this theory tapped into fears of science and the unknown, playing on the anxiety that such a powerful machine might inadvertently invite forces beyond human comprehension. Of course, the LHC's activities have no real connection to any of these wild theories. Located deep underground, far from the path of the eclipse, the collider's research is focused solely on understanding the fundamental nature of matter, space, and time. It is a tool of discovery, not destruction. Building on the LHC's legacy, the next frontier in particle physics promises to answer even deeper questions about the universe's origins and its mysterious components. The next frontier in particle physics. The discovery of the Higgs boson in 2012 was a monumental achievement in particle physics, but it also opened a Pandora's box of new questions. One of the most intriguing inquiries is the role of the Higgs boson during the Big Bang and its influence on the evolution of the universe. What part did it play in shaping the fundamental forces and matter we observe today? Additionally, the Higgs discovery raised questions about the limitations of the standard model of particle physics. Can this elusive particle help explain phenomena like dark matter, or the mysterious imbalance between matter and antimatter in the universe? To answer these questions, physicists are turning to the vast, uncharted territory beyond the standard model, a landscape filled with possibilities yet to be explored. Some theories predict the existence of new, heavier particles that are out of reach for the LHC, but could be detected at much higher energies. Others suggest the existence of lighter, more elusive particles that interact weakly with standard model particles, requiring enormous datasets and sophisticated sensitivity to detect. The Future Circular Collider, FCC, aims to explore this new frontier. Set to be the successor to the LHC, the FCC promises to push the boundaries of our understanding by offering unprecedented precision and energy levels. The FCC's two proposed machines, the FCCE and FCCHH, would explore particle interactions at new scales. The FCCE will be dedicated to precision measurements, running until the mid-2060s, while the FCCHH will reach collision energies of 100 tera-electron volts, aiming to answer deep questions about the universe's structure well into the next century. As the FCC feasibility study continues, scientists are carefully considering everything from technical and financial challenges to environmental impacts. This new collider, with its 90.7 kilometers tunnel, will bring us closer to unlocking the secrets of the universe. Could research at CERN be the key to unlocking the mysteries of dark matter, the origins of the universe, and the fundamental forces that govern everything around us? Let us know your opinion in the comments below.
Blue Grotto is roughly 25 meters wide and 60 meters long, but what really makes it memorable is the lighting. In the cave's underwater section, sunlight filters through a tiny aperture. The entire cavern is filled with a stunning, glowing blue as the light reflects off the water below. The effect is almost magical, and it is what draws people from all over the world to see it. But getting to the Blue Grotto is not as simple as just walking in. The cave's entrance is only about 2 meters wide and just over a meter high at low tide. This means the tide has to be low and the sea calm for visitors to safely enter. Once the conditions are right, you have to lie flat in a small rowboat, usually with only 3 or 4 people. The boatman uses a metal chain to guide the boat inside, pulling it along the walls of the cave. It's a slow, quiet ride, but once inside, the sight is worth it. Inside the cave, there is more to explore. At the back, there are 3 smaller passages leading to a room known as the Room of Names. This space got its name from the many signatures left by visitors over the centuries. The cave also has a few passages that lead deeper into the cliffs, though these are less visited. The Blue Grotto has a rich history too. Back in Roman times, it was used by Emperor Tiberius as his private swimming hole. He moved to Capri in 27 AD and made the cave a part of his luxurious lifestyle. Tiberius even decorated the grotto with statues of sea gods like Neptune and Triton. Some of these statues were recovered from the cave in 1964 and can now be seen in a museum in Anacapri. However, not everything about the grotto is as peaceful as it looks. In 2011, a visitor was seriously injured while entering the cave. It was later determined that the boatman had taken the risk of entering the cave when the sea was too rough. Because of this, swimming in the grotto is now forbidden, as the waters can be dangerous if the conditions aren't just right. The Blue Grotto is a place where nature and history meet. In addition to being a serene and lovely location, it has an air of mystery that leaves a lasting impression. Before we continue with the rest of the video, here is the subscriber's pick for today. In this incredible image, we see 2 divers exploring a mysterious underwater world. The cave is full of rocky walls and sand, giving it a